When we looked at systems of two variables, we learned a few ways to solve them. One of those ways was substitution. When we used substitution, we looked for a variable that was all by itself. So for example, we would have x equals 2y plus 7. So we looked for the variable that's all alone. We're going to do the same thing when we are solving three variable systems using substitution. It's going to take us a little bit more time because we're going to have to find three things, but we're still going to be looking for a variable that's all by itself. If we don't have one, we're going to make one. That lets us know substitution is a good method. Just a reminder that when we write our solution to systems of three variable equations, we need to write them as a ordered triplet. We have an x coordinate, a y coordinate, and a z coordinate, because that's where it is in three-dimensional space. So let's look at a few examples. Here we have a system of equations in three variables, and so there are three equations. I'm going to number them 1, 2, and 3. No matter what method you use to solve these types of equations, you need to make sure you use all three of the equations at least once. That way you know that your solution includes all three planes. Now, I see we have a variable all by itself. Variable x is alone, and we know what x equals. It equals the expression I just underlined. Now, since we have a variable all alone, we can substitute it into one of the other two equations. I'm going to start out by using equations 1 and 3, and I'm going to use substitution. So we have 2 times the value of x, which is y minus 4z minus 6, plus y plus 3z equals negative 1. Now, oops, I shouldn't have changed in the middle. We end up with 2y minus 8z minus 12 plus y plus 3z equals negative 1. Now we can use some of the solving techniques we did before. I'm going to combine like terms, and I'm also going to take care of this negative 12. I'm going to add 12 to both sides and move it to the other side. So that way we end up with a nice equation like 3y minus 5z equals 11. Now we can't solve it any further because we still have two variables in that problem. However, we can find another equation with two variables and then continue to solve from there. So we used equations 1 and 3. Now we need to use equation 2 at some point. So I'm going to go ahead and use equations 2 and 3 and use substitution again. So I'm going to switch colors. Hang on a second. Alright, so we're using 2 and 3, and we're going to substitute for x. So I'm going to take x out of the equation, and in place of x, I'm going to write y minus 4z minus 6. Then we'll continue the rest of the equation, plus 2y plus 3z equals 1. Now we can distribute. We'll end up with 4y minus 16z minus 24 plus 2y plus 3z equals 1. Just like I did before, I'm going to combine like terms, and I'm going to move the number to the other side. So I'm going to combine my y's, I'm going to combine my z's, and then I'm going to move that negative 24. I'm going to add 24 to both sides. That way I end up with 6y minus 13z equals 25. So if we look at what we're left with right now, we have 3y minus 5z equals 11, and we have 6y minus 13z equals 25. This is a system of two variables that I can solve using substitution or elimination. I'm going to move to the next page because I'm totally running out of space, and this way you can kind of see what's going on. Okay, I went ahead and copied the original equation and the new equation that we got so that we had more room to do our work. We have a two-variable system at this point, so we need to use either substitution or elimination to simplify it. So it looks like we can get opposites with our y's, and that's what I'm going to do. I'm going to multiply the top equation by -2, so I end up with -6y, there's my opposite, plus 10z equals -22. Alright, now we're ready to solve this thing. So I'm going to solve it using these bottom two equations. I'm going to combine them. So we get -3z equals 3. Divide both sides and we get z equals -1. So now I have one of the three numbers I need for my final answer. I'm going to go ahead and put z as -1 down in my ordered triplet. Now we have two more variables we still have to find. We have to find x and we have to find y. We can find y by using our smaller system of equations. So we can substitute for z and find y. I'm going to use the 6 equation. So 6y minus 13 times -1 equals 25. 6y plus 13 equals 25. Subtract 13 from both sides, so we get 6y equals 12. Divide both sides, and we get y equals 2. So I'm going to go ahead and put that where that's supposed to go. So we know x and we know y. Well, now we need to, we know y and we know z. We don't know x. We need to find x. Now we have to go back to our original system. Our original system is the only place where I see any equations with x's in them, and I am going to use this bottom one. So we need to substitute for y and substitute for z so that we can find x. X equals y minus 4z minus 6. And remember that it looks like y is 2 and z is -1. So then it's just a matter of using your math. We get x equals 2 plus 4 minus 6. So x equals 0. Now we have our final solution. I'm going to put a 0 where x goes. And our answer is x is 0, y is 2, and z is -1. That means these three planes intersect at that point in 3 dimensions. So we can solve systems of 3 variables using substitution just like we did before. The big difference is that we end up with a smaller 2-variable system that we need to solve. After we do that, it's just a matter of substituting back in and plugging in to find the missing variables. Alright, another system of 3 variables, and we're going to think about using substitution. For substitution, we need to have a variable all by itself. Do we have a variable by itself? We actually don't, but we can certainly get a variable all by itself pretty quickly in any of the 3 equations. I'm going to focus on this top one. I see that all I need to do is add 5 to both sides, and I'm going to have z. So z equals x plus 4y plus 5. Now that I have this variable all by itself, I can substitute for z. Now, again, we have 3 equations. We need to use all 3 of them at some point. I'm using equation number 1, and we can use either of the other 2 equations to begin our solving process. Since it's the next one, I'm just going to start with number 2. We're going to substitute in for z. That means you're going to rewrite the equation. Everything stays the same except for z. You take z out, and in its place, you substitute what z equals. In this case, z equals x plus 4y plus 5. Now you just need to use those basic skills we learned about solving using distribution and combining like terms. Let's distribute, combine like terms. I see x's, I see y's, and I'm going to go ahead and subtract 15 from both sides as well while I'm thinking about it. So we're going to end up with 4x plus 14y equals -6. So we have one of the 2 variable equations, but we need a second one, and we haven't used the equation number 3. So So that's what I'm going to do now. I'm going to substitute into equation number 3. So again, I am going to write the equation as it is, except for removing z. Z is what's getting substituted in this problem. And in z's place, we're going to substitute x plus 4y plus 5. Now again, we're going to use our distribution and combining like terms. So when we distribute, and just like before, I'm going to combine these, and I'm going to move that 10 over to the other side by subtracting 10 to both sides. So now we have 3x plus 11y equals negative 5. So if we look kind of closely at what we have now, we have an equation with two variables and another equation with the same two variables. So we can create a two-variable system, which we can solve using either elimination or substitution. I'm going to move to another slide because I've used up a lot of space, but I'm going to keep the three-variable system, and then I'm going to rewrite this two-variable system for us. Alright, looking at our two-variable system, I think I'm going to use elimination on this one. I'm going to try to eliminate the x's. Those are smaller numbers. I have 4 and 3, so opposites would probably be 12 and negative 12. Doesn't matter which you make the negative one, I'm going to make the top negative. So I'm going to multiply it by negative 3. I'm going to make the next one the positive 12, so I'm going to multiply by 4. This way we're going to end up with opposites for our x's. So we're going to end up with negative 12x minus 42y equals positive 18. Then in the next one, 12x plus 44y equals negative 20. Now I have opposites, I can go ahead and solve. X's will cancel. I'm going to end up with 2y, watch your signs, equals negative 2. So y equals negative 1. So remember, our final answer is going to be written in an ordered triplet, and so negative 1 is y. I'm going to put it in the right place right away before I forget. So we have y, but we need x and z. I'm going to use one of our two variable equations to find x. That'll be a little bit simpler. Doesn't matter which one you use. I'm going to choose to use that one with the 3. So 3x plus 11 times y, which is negative 1, equals negative 5. 3x minus 11 equals negative 5. Add 11 to both sides, so you get 3x equals 6, and we get x equals 2. So I'm going to go ahead and write that in the right place as well. So we have x, we have y, now we need to find z. I'm going to use one of my original equations to find z. Might as well just use the top one. So we can plug in the number for x, we can plug in the number for y, and then we just need to use some algebra to find z. So z minus 5 is x, which is 2, plus 4 times y, which is negative 1. So z minus 5 is 2 minus 4. Z minus 5 is negative 2. Add 5 to both sides, so you get z is 3. Add that to your ordered triplet, and we have our final answer. These planes intersect at the point 2, negative 1, 3. One more example for us to try substitution on. Again, I don't have a variable by itself, but we can make a variable by itself in the top equation. It does not matter which variable you get alone, as long as you're consistent. So it looks like I could pretty easily get y or z alone. I'm going to get y alone just because we haven't done that yet. So I'm going to add x to both sides and subtract z from both sides. So we get y equals, remember I added x, subtracted z, and then the 8 stays as it is. So that's the equation I'm going to use for substituting. I have y by itself, so I'm going to substitute x minus z plus 8. So we can use, remember we have to use all three of the equations at some point. We have to start out with two of them. I'm going to use equation 1, and we might as well use equation 2 for the other one. So we're going to substitute for y, because that's what I solved for. So 2x minus 2 times whatever y is, minus 2z equals negative 16. So again, we're going to substitute that in for y. So we get x minus z plus 8. Now we need to use our basic solving skills, so we're going to distribute. Oops, that's not plus 8, it's minus 16. Alright, now we're going to combine like terms. 2x minus 2x, positive 2z, negative 2z. I'll leave the 16 there for now. So 2x and negative 2x cancel each other out. 2z and negative 2z also cancel out. So I'm left with negative 16 equals negative 16. Uh-oh. This is one of those special cases. This is where we ask ourselves, when does the number negative 16 equal the number negative 16? All the time. So this problem actually has infinite solutions. I'm going to go ahead and write infinite solutions. What that means is that these planes intersect on a line, and lines go forever, so all points on that line would make it true. So this was solving using substitution. We also learned another method of solving two variable systems, which was called elimination, and we are going to look a little bit more at solving three variable systems with elimination in another video.